Hello. In this section, we are going to introduce the topic of the comparison tests. We have actually already seen a comparison test for integrals, and we are coming back to that idea. We're going to use that same test, but for series. So the big idea is, suppose we have an infinite series and we want to compare it to another infinite series that's known to be convergent or divergent. So if we know it's convergent or divergent, very likely this is a P series or a geometric series, because those are really quick and easy to tell. Does this converge or does this diverge? So we will most often do these comparison tests to P series or geometric series. And we actually get two tests that we'll just generically call the comparison tests. There is the direct comparison test and the limit comparison test. The direct comparison test, the first one we're going to look at, is the same as the integral comparison test. It says, suppose we have a series AN and a series BN that both have positive terms. Then, first, if the sequence AN is less than or equal to the sequence BN, so dropping the series, we're just looking at the sequences now. So term by term, AN is smaller than BN. And we know the series of BN converges. Then the series for AN also converges. When we were talking about the integral test, the picture was drawn of, suppose I have this function that converges, and I have another function that's smaller than it. That is the idea here, is if I have a big thing that goes to a number, then if there's something that is absolutely smaller than it, then that will also converge. The second is the reverse. If we have that AN is bigger than BN and the series BN diverges, then the series of AN also diverges. And this would be, for our integral comparison test, was if these functions were switched. If I had f of x being my bigger function and g of x being my smaller function, and I knew the smaller function integral diverged, then the bigger integral also had to diverge. So if we have a small thing diverging, then the big thing also diverges. If the big thing converges, the small thing also converges. So there becomes this process we can use for this direct comparison test. It is going to be the process that first we check for positive terms. This is most often just stating, yeah, my series is all positive, or the sequence is completely positive. But does need to be acknowledged, because we're going to get to some tests where they're not always all positive. So we just need to check that. Second, we want to find a comparison test, a comparison series. This is typically a p-series or a geometric series, as stated earlier. So we're going to look at our series and see, is there a geometric series or a p-series that this is kind of close to, that this is kind of reminiscent of? 3 is then, now we've found a p-series and a geometric series to compare to. Well, does that series converge or diverge based on the p-series and geometric series tests? We want to determine if what we're comparing to converges or diverges. So four is then to run the test. Sometimes running the test happens while finding the comparison series. But if it doesn't happen while running the comparison, finding the comparison series, we then have to run the test. This set of process steps is the same for both tests we're going to talk about today. So one of them, running the test, is its own thing. The other, sometimes it happens along the way. So sometimes that happens in the second step. And then the fifth part, once we run the test, is our conclusion. So let's run through these steps with the series n over 1 plus 2n cubed. First, check that this is positive. So for n bigger than 1 or equal to 1, is n over 1 plus 2n cubed positive? Yes, it is, because that numerator will always be bigger than 1. The denominator will always be bigger than 3. So positive over positive is going to be positive. So that is true. Now we want to find something to compare to. So we're looking at 1 plus 2n cubed. And we want to compare it to something. And we're wanting to compare it to a geometric series or a p-series. So looking at this, if I look at these big ideas of what's going on, n over 2n cubed, that itself is a sequence that fits into a p-series form. So what we'd want to compare it to is just those big term things. And simplifying that down, n over 2n cubed is 1 over 2n squared. So we're going to compare to that big picture series 1 over 2n squared. So we found what we want to compare it to, 1 over 2n squared. Now we want to determine, does that converge or diverge? This converges because it's a p-series. And the p-series test says that a p-series converges if p, which in this case is 2, the exponent of 2, is bigger than 1. So we are comparing to something that converges. Now we want to run the test. And this is something we could have done a little bit earlier when we were finding our series to compare to. And that is, for this test, we want to know, how do an and bn compare to each other? Which sequence is bigger? Well, between an and bn, the only thing that changes is that denominator. In the case of an, that denominator is bigger than the denominator of bn. And for fractions, the bigger the denominator, the smaller the fraction. So n over 1 plus 2n cubed is smaller than n over 2n cubed. This means we have this case of 1. We have an is smaller than bn, and the series of bn converges. So, since we have this first case, we can now make our conclusion that the series an also converges. So that means our series n over 1 plus 2n cubed from n equals 1 to infinity converges, remember series converges or diverges, by the test we just did, direct comparison test. And then a reason why, all of our reasoning is above, but the big reason why is since what we compared to also converges. So there is our first example. In the next video, we'll take a look at 2 more examples of using the direct comparison test.